Hello, everyone. My name is Maria, and I'm the CTO at Tinder. So we're all here today curious about data migration. Am I right? And before we dive deep into the best practices, the lessons learned, the nightmares, I want to start this talk by sharing the story of how it all got started. The question, why did we need to do such a massive data migration? So for a combination of reasons, let's just call it legacy, that we had a hybrid environment. A lot of our services are running on AWS, but we have a very core piece of the entire runtime process, hosting one of our largest data set, very mission critical, separate at a data center. And after a few months of investigating, understanding the architecture and the benefits and cost, that I decided that it was necessary to migrate the data off this data center onto AWS. And this is a decision, it wasn't made lightly. And as a CTO of the company, I had to present to the board. And so this is kind of the boardroom story. So I went up to the board, I put together this presentation, and in summary, it was 3 words: downtime, performance, and cost. The previous setup in this situation, that we were suffering outages here and there, and it really wasn't something we felt like we could mitigate through engineering excellence. And in terms of performance, as you can imagine, just data transferring across the wire is just pure physics, that when you have data coming in and out in runtime, and it's pegging on latency and hampering our user experience. And the third part is cost, because you are paying for all the data transfer and additional maintenance and support at this data center that's hosting the user data. So that led to this decision. And so if anyone here is planning or considering thinking about that, I think the first question we need to have a very clear answer is why? Why do we need to do that? And after we've committed of, yes, this is the right thing to do, let's do it, it wasn't easy. Frankly, I was a little scared because, of course, I asked the board, okay, we're gonna do migration, and this is in the critical path of our runtime services. Can I go dark for a bit? Right, I actually already knew the answer is no, but I thought I would ask anyways. And then basically the requirement is, yes, you can migrate all day long, but I want 0 downtime, right? And that makes, right, all the challenges surface. Let's go to the next slide. Yeah. So just in case you don't know, I want to do a quick intro of Tinder. So who here has heard of Tinder? Yeah, everyone? Yeah. So what is Tinder? Tinder is a platform to connect people all over the world to make a new connection. Right, so we all use Facebook, Instagram, and so forth, right? So those social networks are important because it keeps us connected with, friends, cousins, right? People you went to elementary school. That's your network of social connections, and that's great. So I know what my cousin had for lunch yesterday. But how about the people you don't yet know? Right? How about a new connection and have a conversation you would not have had otherwise? And this is what Tinder is for. And so if you've known Tinder, you probably are familiar with the swipe left and swipe right. And it looks like such a simple app, right? It's just this little app. You see photos and you swipe, and how hard could that be? So the Tinder product design, I use this term iceberg product, meaning the user interface is very minimalist and very intuitive for anyone to use. And that was an intention and also a constraint. We hide all of the complexity beneath the surface. And if you look at our scale, and scale, again, makes all the difference, that we're processing 1.6 billion swipes a day. Our users are all over the world. So we process over 300 million personalized geospatial queries in terms of when you open the app. Actually, there's a very complex data retrieval and computation and ranking. And the last step is serving and rendering. We're also a very global company. We're in 190 countries, and the products are in more than 40 languages. Yeah. So now compounding, massive amount of data, right? Global footprint, and we want to migrate all these data from some data center somewhere on East Coast onto the cloud. In this case, AWS. This is all great. But who's going to do the work? So again, a little story of the first time I met with JunYoung at this coffee shop called Euro Cafe in West Hollywood. And a little bit background of JunYoung, that he went to the Seoul National University in South Korea, and then went to CMU, and then went to USC and got his PhD in computer science, doing machine learning, robotics, database systems. And when I saw his resume, what I see is someone who's not afraid of a challenge. More so, he's probably energized by challenges. So when we first met, I was extending an offer, and I was very honest. I said, JunYoung, I promise you, you won't be bored. And I think and he wasn't scared. He said, I'm ready to do this. Long story short, it took us months to get to a complete migration. Now we're 100% on the new system. And going back to the original concern, downtime, performance, and cost, that we benefited in all three and addressed all of the issues. So next, I'll have JunYoung walk you through this journey that we had gone through of a massive migration with zero downtime. Yeah.
Thank you, Maria.
Sure.
Thank you again, Maria, for a nice introduction. I'm very happy to be here today to have an opportunity to share how Tinder really handled massive data migration with zero downtime. As Maria already gave a context or story at a higher level, the building efficient and reliable backend service is really tough. And one of the core challenges coming out from that is choosing the right data stores. So these days, it becomes more and more complex. You have more choices coming out in the market, and you now have to understand what's the characteristic of each data stores and what's the benefit you can actually get maximally from it. And also, you need to look at your data and then see what is a good fit. Like, let's say one data store is perfectly good, but if that is not working on my data set, that's basically useless, right? So obviously, we have to understand what's the requirement coming out naturally from the data set, and choosing the right data stores based on your requirement is critical. But even further, the requirement around the data store and then data can be changed over time. So for instance, your data scale might be changed. If you just keep extending your services, going to different global markets, your data scale can be significantly increased. At the same time, data access patterns on your data set can be changed, which is often not controllable from your side at all. So which is a really, really tough problem. This is where the massive data migration actually comes into play, and then you really have to consider we have to do the massive migrations between different data stores, or sometimes you need to optimize the data model or access pattern and then schema and so forth. And then that's a great opportunity to actually take that. But at the same time, it's really tough. As again, Maria mentioned that the handling the data migration is naturally really tough. Why is that? So before getting into the details, let me actually prop one quick picture for that. So if you look at this is a very simple picture one pilot is trying to fix a problem in the airplane while they're actually operating it in the air. That means this is really well capturing where we are in the real world. We cannot really simply stop operating our services, which is really degrading the user experiences. Then what can we do? We want to do this massive migration over time while keeping the service up to date and then up. So that's where all the challenges are coming in around the massive data migration in this situation. Then why do we care about the massive migration again? Like, why do we need this data migration over time? What do we want to achieve from that? So I just showed you the one acronym that is called PRICES. I just personally really like it. You can imagine this is a somewhat abstract way capturing the migration is not coming in free. It's really pricey. But if you successfully handle that at the end, it comes back with really high reward for you. Getting into a little more details, these prices actually mean certain terms, including performance, reliability, impact, cost, efficiency, and then scalability. I think each term in this chart is self-explanatory itself, but let me just explain very briefly for each term. For instance, performance, we really want to decrease the latency. What would be the right data stores we want to use? Where to move? Reliability, I want to increase data availability over time and then really reduce the downtime from the service. What would be a good choice for that? Once you choose the right data stores, probably you have a lot more flexibility and then freedom to build extra features on top in a much, much faster speed. Then you will actually give back to much better user impact in real world. And at the same time, by optimizing data model and data access pattern, you will see significant cost reduction by handling this migration over time. And that is really critical because we can actually make our financial teams over time very happy. When I actually say the efficiency in this chart, it's not simply the service efficiency only. You can imagine we are engineers. We actually need to build something real world. And you will see you need to choose the right data model and data stores, really building services on top, testing, debugging, releasing those features in the real world. You have to often recycle and then repeat this many, many times. And simply choosing the right data store and then data model will reduce these efforts a lot. Lastly, the scalability. Obviously, I want to choose the right data stores that is by nature support the horizontal scalability regardless of the data scale I want to store. So this is kind of like the goal we actually overall want to achieve from the data migration. And then what do we do? So this is what we did. Obviously, we chose the DynamoDB as a best match for us. And we love each other. And then rest of the session, I will actually focus on why the DynamoDB was a good fit for us based on our characteristic properties, and at the same time, discover a little more details about the data migration framework we built to handle this migration in a very seamless way, and then sharing a couple of learning and best practice, and then wrap up the session. I believe like most of the audience in this session is already familiar to DynamoDB and then related features. So I will not really repeat too much, but I just point out a couple of points why that was really attractive to us. For instance, documentation really claims that shows the consistent low latency performances. Really? Well, I usually very skeptical to believe this documentation that's just by itself. So we really test it out and then see how it works. And it was really consistent. So I'll show the result at the end, a little more details. Another big point for us is it really supports the seamless scalability based on the provision throughput concept with auto-scaling with really low administration cost. So it actually helps us to achieve the development efficiency that I mentioned in the earlier slide, just like simply choosing the DynamoDB. And one additional point is low cost. We can actually optimize a lot and play with that with the provision throughput, utilizing auto-scaling, reserve capacity, and so forth. Then you can actually optimize cost over time as well. Another feature on top of DynamoDB is obviously we are using more and more streams and triggers on top. These Dynamo streams comes into the play to actually sync up all the data chains in your main critical table and then push out the data into different places automatically. And then triggers also, if you're using Lambda functions, that actually for free, you can just push out those events happening through the streams, and then you only need to pay where you're actually using the Lambda function only. So based on that background, I will actually get into a little more details about the data migration framework we actually built and then execute. From this side, I'm mainly focusing on like visualizing how we actually built with what flow and what are the key point and then challenges you actually met. And then I will skip too much technical details throughout this session, but I'm happy to discuss offline if you want to hear more. So let's say you have your own existing services, each app, usually running on EC2, the gateway services, anything else. And it actually has your own source data stores. It can be Mongo, it can be Dynamo, it can be less cache, and so forth, anything. And you actually serve your entire product traffic on top. Now, I figured, OK, I want to move some of the data to Dynamo. What should I do first? Obviously, you need to set up the Dynamo table first. So you can actually use CloudFormation or any of the different CLI console. You can just create it. And then you can actually start writing to both source and target table. Whenever I say fork operations in this session, that actually means the shadow operations, which should be non-blocking in prod. But at the same time, we have to really handle these reliable error handlings on those shadow operations. So once you turn it on the fork write, what that means is from that point, we actually start from the empty data store, but you now catching up all the incoming updates in both source and target table. And whenever you see the failure, still you need to handle somehow. How can we handle that? So we actually using the DynamoDB as a queue. I mean, you can choose different stories like SQSQ or Kinesis and so forth, and then storing those things and then catching up. But what you can do is pushing those failed cases with ID and timestamp and so forth, turning on the streams, and then you can actually enable the data sync flow. Now, you can actually maintain your own worker set. You still have more freedom. You can just implement it as a Lambda. You can just using the KCA workers running on EC2. Obviously, you want to utilize spot instances to save cost a lot more. So the good things for here is the core business logic, regardless of how you actually build the worker, is shareable. So once you build in a form, you can actually move that logic into the different form, just simply running them based on your requirement change. Then you will see that now, OK, now I have a lot more reliable failure handling cases. So I can believe now more between source and target tables are in a sync, at least for the incoming request. But still, the missing point is here, how we handle the legacy data that has not been touched by the product traffic yet. So we actually have to offline data migration. This is more like a one-time stuff, if that is ideal. But you can just run multiple times as you want. But this offline migration, essentially what they do is scanning through entire source table or data, applying the data transformation in a batch way, pushing out to your target table. So again, one of the key things here is from the offline migration, you might see the failure too. We cannot ignore them. How can we link them then? You can just reusing the existing features and then simply just sending those failure case to the queue. Then you can imagine now you don't really have to worry about any of the failed cases. All of those failed cases like stored in the queue will be automatically caught up. And then eventually you will see the updates in the target table. So one more key point I really want to emphasize here is often you might need to move your data not only within the same VPC in AWS, you might need to move your data center to your VPC or some other outside vendor too. Then we can probably set up the direct connect to speed up and then reduce the latency and then make more reliable for that case too. Now, we can see that now, like after running this offline migration, all of those data, including offline legacy data and then incoming data, are in sync. How do we validate them? In the beginning, we thought maybe offline validation might be good enough. What that means is we just like going through the entire source table and then fetching the target table from the target stores, new stores, and then really compare. And then check what is the ratio of the inconsistency and so forth. This is great in terms of static way. You will actually go through entire data, regardless of whether there is access or not, just like checking all of the data and then see how it works. But we actually realized one problem in doing these migrations. What happened here is we actually had a small bug in fork writes logic. It actually kept introducing noise on the real data, and it was rebuilt a lot later time. So if you just rely on this offline validation at one time with a snapshot version, you might not be rebuilt for that. So, okay, what would be a good way to actually resolve that then? So we introduced the online validation on top. Same way, we're actually turning on the fork read. That means still this is shadow operation, just reading additionally from the target table based on the prod traffic. We really compare the data and then making sure the served data from the target table is ready to go. So this is really good in terms of catching the dynamic changes that is currently happening in the real data in specific target table. And you will see this both combination of offline and online validation is really capturing all those aspects of static and dynamic validation purposes. One caveat here is fork operation is great, but it's not free again. You have to maintain that additional logic and then really have to run them. That requires additional resource consumption. So what we usually do is we're controlling this traffic with etcd cluster that is supporting from the ops team, controlling gradually how much traffic we want to sending, and then fetching the data. So we gradually turning on the fork read while carefully monitoring the stats in apps so that we don't really interrupt any of the prod operation ongoing. And also at the same time, we actually handle this online validation in a more selective way. Like, why do you need to validate 100%? If we just believe this is good, then we can probably turn it on 10% validation rate only and just like see how it goes. Another key thing is during the validation is you really have to define your success metrics very, very definite way. They usually have to be measurable and then quantifiable. Example of the validation success metric will be latency, for instance. How fast should it be? Or what about the error rate you might see? What about cost reduction you might want to expect to see? Something like that. So once you actually match up with your own success metrics, once you feel good, okay, I'm ready to go, then you actually enter the final stage. You actually cut the cutover code. So we handle this cutover traffic with a lot more careful, but in the same way. So we actually gradually sending new traffics, let's say n% of traffic to the target table. Now you can imagine all those data served with n% traffic from the target table. This is great. Once you have a great extent of the validation in the previous steps, you might be okay with that. So we really just straightly turn it on the cutover and then see how it goes over time. And it actually, we realized it was not that good enough. The reason being is sometimes the issue, again, is not immediately popped up. We extensively validated for a certain time, but later we found one of the edge cases that is actually happening right after cutover, and it was not really revealed for weeks. Then what should we do? And it actually happened to us too. Like in 2 weeks, for instance, one of the purchase team actually asked us, hey, this data looks a little weird. What's going on? And we started investigating, oh, God, there was some logic errors. And it was really hard to find because there was real edge cases, but we cannot really ignore them. So we're just thinking about, OK, maybe we have to be coming up with some more rollback plans for that. So that's where we're actually setting up this, the reusing basically the queue, and then still turning on the fork write, even under the cutover mode, so that you can imagine these two data stores are completely in sync between source and target over time. And then great thing is you can actually reuse all of those existing resources as they are. You don't have to rebuild anything. Only thing you need to change is just change the data transformation and then source and end target point. And great thing here is once you have all this ready, then you can actually roll back and proceed in cutover based on your confidence and progress level. And then you can really control, like, OK, how quickly I want to go. And eventually, once you feel all the validation is successful under the cutover even, we can actually cutting over 100% and declare the victory, and then you are now ready to tear down the resources. So this is, again, capturing the overall migration frame. We handle that in a higher level, visual level. So there are much more the detailed challenges, and then the implementation details. We can actually share that. Again, feel free to talk to me if you are interested to hear more. So that would be great to share that. Based on that, the migration framework. So far we discussed about the challenges, what we are seeing from this data migration, why that is important, why that is hard, what do we want to achieve, how did we achieve, what did we learn from it. Before getting into the key learning points, I will actually share quick stats, what we achieved. By the way, for the clarification, this is only covering the Mongo to Dynamo migration case. So this is not including all the other migration we are currently handling. So we moved the total data size more than 25 billion, actually close to 30 terabytes, the data from Mongo to Dynamo. And essentially, we actually achieved the cost reduction more than by 60%. That means simply moving your data, optimizing data model a little bit on top, massaging them, you only paying less than 40% of cost compared to the previous situation. This is great. So you can also utilizing the auto scaling and reserved capacity. Again, the reserved capacity is more like a reserved instance concept. You just like pay upfront fee for minimum usage level you actually define, and just like paying with a significantly reduced cost for project throughput. So you can essentially utilizing these two concepts in a combination way and achieve a lot higher cost reduction more. In terms of performance gain, really, we actually saw the read and then write. It's really very consistent in terms of the performance gain, and then single-digit milliseconds for most of the query case. One caveat here is Dynamo is great when you scale the data while keeping the data size concise. What that means is it really matters more item size that you're actually maintaining, not really the data scale you need to store. You will see the same consistency level of the performance when you have 100 items versus 3 billion of data. But if your item size is 1K versus 400K, that is the limit of the DynamoDB, that will be impacting your performances. But obviously, it's inevitable. You will see the same thing in all the different data stores. So just keep that in mind. That's a great thing you actually need to keep. For learning part, I will probably break down into 3 sessions. Before starting the migration, what do we want to know? Again, as I mentioned, that the first thing you really need to understand what's the situation, what's the limitation you're actually seeing in the source data stores you want to migrate, and then what's the potential target stores you want to use. What's the difference in this case? So for instance, in our case, we actually look into the Mongo and Dynamo specifically, see how it works. It sounds very similar at the higher level, but indeed, when you actually dig into more, you will see many different assumption differences. It's very implicit. That is sometimes very problematic. So as an example, for instance, when we actually build the app services, all of the API is accessing the exactly same way, regardless of data stores. And it turned out the way to actually handle update and partial update, delete, and create is very different between Mongo and Dynamo. And it started causing the issue, although we keep the same data model. So that's just one simple example, but you will see there are many different underlying differences you need to understand first, what you need to be prepared to change in your app side too. And obviously, again, this data migration is a great opportunity to optimize data model and then schema. Particularly in Dynamo, one of the key things you need to consider is the key design. So hash plus range key, that is the primary key we actually maintain, or partition key and sort key. What would be the best way to distribute your data in a more even way? What would be the good design for global security index you want to maintain? What all of the data you want to project to the global security index table from the main table? Really depending on just one decision for that, it will determine your entire cost and performance overall. As an example, again, GSI, in general, we just project the entire the field into the GSI table. What's happening is whenever you write something in your main table, all of those changes will be propagated to the GSI unnecessarily, although you don't need that data. Then it's actually multiply n times of the cost for the writing, depending on the number of GSI you're actually maintaining. Another thing is the Dynamo really supported the schema list. That's great. And then we can actually store different types of data over time. We don't really have to change it too much. But at the same time, if you don't really carefully design the schema enforcement from your service side, you might lose the ability to track down the quality of the data over time. So this is something you also have to keep in mind. Okay, what is a good design of the data model, and specifically key design, trying to match up with your data access pattern coming from real traffic. And lastly, again, we really need to carefully define success metrics in more quantified way, and that will be the key to evaluate your overall migration efforts and then decide whether you are good to go. Once you are ready, again, then based on the defined success metrics, we really want to evaluate the entire migration in a very careful way. And in our case, it turned out this two-way extended data validation, including online and offline, works really well. And then key here is you have to make a framework that is allowing you to validate over time multiple times whenever you need. Another thing is whenever you do the validation, you have to be prepared to collect all the metrics coming from that. So we actually get a lot of help from ops team to actually set up reliable metrics tracking and then logging system. All those values are coming in, and this validation, I can actually confidently believe, okay, we are ready in terms of the objective value we're actually seeing from the traffic. Another thing is the failure can happen any time point during the migration procedure. You really have to plan for failures and design the system to overcome or mitigate those impacts. Again, one of the examples that I mentioned earlier is in the cutover, we didn't really consider about the sync between source and target table because we believe we are now ready to cut over. Just switching the traffic over time to the target table will be good. Sometimes we are very in a hurry, sometimes, or overconfident. We don't really want to do that. So we really come up with a systematic way to mitigate those failures. As long as we are prepared, you should be okay. So you don't really have to worry about the failures. Then you can actually going back and forth a little bit, just controlling your schedule and then pace a little bit, and then you can still achieve the same goal. Once you're done with the migration, reach to the 100% cutover, it's not done yet. What will be the follow-up? You really need to set up the data backup correctly. Fortunately, in AWS, we were able to use the AWS Amazon Data Pipeline to set up the export and import to S3 using EMR from the Dynamo based on some given frequency. But now you have the opportunity to use many backup services from Dynamo too, which is great. So you don't really worry about the backup anymore. And as long as you actually push it out to the Dynamo, you have all the backups whenever you need based on your frequency and the requirement. At the same time, you can actually turn on the streams whenever you want to push out those changes and synchronize updates into different data stores. Another big shout to the ops team is they actually suggest us to actually apply CloudFormation IAM throughout this migration procedure. We actually prefer a quicker way in general engineers. Just I want to create the table using CLI and then console. Why do we need to care about the CloudFormation? But it's not true. Once you start the CloudFormation, you actually have a lot more ability to control your history of the changes of the Dynamo table, controlling the provision throughput in a more systematic way, and then you can actually rebuild whenever you need that in the exactly same way based on DSL. Another thing is you can actually utilize IAM for controlling the accessibility. This is great because not only just controlling making entire apps more secure, but at the same time, you explicitly set which services can talk to which table. Then based on the information, you can understand data access pattern a lot better way. Let's say I only have the accessibility from service A and B and C talking to table 1. Then when I actually analyze table 1 data access pattern, I only need to talk about service A and B and C. That's it. You only need to understand the QPS coming from those services. I don't really have to worry about some other cases because they'll be rejected. Lastly, don't forget to tear down resources once you're done. So this is great for reducing your cost. There are more learning points, but we just summarize that for the sake of time. But again, we'll be happy to share more over time as time allows. I also want to cover some of the best practices we actually observed from the DynamoDB. There are many different best practices, but I will just focus on one thing. How do you want to maintain or manage dynamo throughput over time? This is really hard problem. We often just using the auto scaling. That's great for predictable data, predictable trap patterns case. But sometimes you cannot really control your data access pattern from real world or real user cases. And even for us, we actually see a lot of spiky pattern of traffic coming in or completely unpredictable access pattern might happen at some point. And in that case, auto scale is not good enough because usually that is happening in reactive manner. They try to catching up after the fact. If you see the changes very gradually over time, this auto scaling works really good. You don't really have to worry about too much. But imagine your traffic pattern change is too sharp and then too abrupt. Then this auto scaling never catching up those changes. Then you will continue to see the problems from hot shard and then throttle request. One way to solve that is really set high provision throughput. I don't care. Then it will cost a lot. So it's not really ideal case. So this hot shard issue is one of the critical points caused by auto scaling or access pattern at the same time the key design you're actually putting in. As I mentioned earlier, the key design means the primary key design of the hash key and the range key combination is a key thing is how to control distribution of the data across the physical partitions in DynamoDB. But ideally speaking, or practically speaking, it's not possible to match up perfectly based on the data access pattern you might not even see yet. I mean, you might be able to come up with or imagine based on predictions. Looking at the history data, maybe this might be happening in terms of traffic patterns. I might be able to distribute the data in that sense, but what happened that is changing again. It's not that easy to change the key setup. So obviously, we will see the hot shot issue in an inevitable way. That actually means you actually start seeing the throughput requests that actually degrade your performance a lot, and eventually you will start seeing the errors. And that is actually coming from both read and write, and this is something we actually suggest. For read case, let's say your service is suddenly just like sending the request to the DynamoDB, hey, give me all the data, I need them right now. And that actually caused a hot shot issue. Then you can actually maintain additional cache layer in between. It can be anything. This is just an example. It can be DAX, it can be AWS cache, it can be a combination of them. And this cache layer choice is really depending on your requirement. And imagine once you have this additional cache layer, most of the hot data you will most frequently access, that is already cached. Then that is actually covered by cache most of the cases, and you only need to send down the cache missed traffic to the DynamoDB. And you only need to set really low provision throughput on it. Let me break down some of the use cases, how we actually utilize them more. Let's say I really want to get fastest speed for the read, but I'm OK maintaining my cache logic in a side. Then less cache will be the best way. You can imagine I set up the less cache. From your service side, you actually, whenever you receive the read request, send a request to less cache first. Once you cache it, just return it. If not, now you're actually sending back to the DynamoDB. That's a fallback search. Once you fetch the data, you backfill and then return it. One thing we observed that in practice is less cache is really showing very, very good performances regardless of the data size. For example, in most of the cases in our data, P even 90, latency was around 1 millisecond. It's great. It's very consistent. But obviously, the downside here is you have to maintain your own cache handling logic in your service side, which is burdensome. What do we want to do if I don't want to do that? So another use case is coming in this way. I still want to speed up the read compared to the Dynamo speed, but I don't really want to maintain any additional logic. Then DAX will be the best case for that. One thing in GA version of DAX is really you don't have to change anything. You just need to set up the DAX cluster and set the configurations of the endpoint of DAX in your Dynamo SDK, just accessing in the exactly same way. So literally for us, we're just adding one line. And the other logic is working perfectly as it is. So all of them is very transparent. Now you can imagine is how does it work is internally it's a very similar way. You just send a request, but implicitly sending to the DAX first. If there is cache hit, immediately return them. If not, then now you're actually sending down to the DynamoDB, fallback, like backfill, and then return it. But that is overall, the procedure is actually automatically handled by DAX. So from your point, you don't really need to maintain any of the additional logic, which is great. But at the same time, you can actually achieve the better speed. One thing I also want to mention here is less cache in the DAX is not exclusive. It's really like choice of how much you want to boost your speed. And the usage pattern is quite different. Also, another comparison point between less cache and DAX is price model. Usually, the DAX instance is more expensive compared to less cache for the same size, but you don't really need to maintain explicit replica set in DAX. They're just following the same model of the three availability zone distribution like DynamoDB. So you only need to create the size of the instances based on the primary data you actually only need to store. Then they will handle the replicas for free. As opposed to less cache, you have to really maintain explicit all the replica set if you want to. So in general, we see huge cost reductions by using the DAX as opposed to less cache, but obviously the downside is less cache is faster than DAX. So again, just keep that in mind and then see what is the best requirement and then use cases for you, and that's how you actually go. What about I want to get the read in the fastest way, but I also want to speed up the backfill as well. This is like one simple case. I just demonstrated, but you can find many more different combinations. You can actually hit the less cache. Now you also need to maintain the business logic in your app side, but in this case, even for the cache miss case, you can even speed up. Then really depending on what is cache hit rate in your system, let's say 50% of cache hit rate, now the rest of the 50% cache miss case was really slow previously, but now it was automatically boosted by DAX. So again, as a recap, you actually hit the less cache from your business logic, return if the cache hit. If there is cache miss, now you're actually talking to DynamoDB through the DAX endpoint. Then you actually have two layers of the cache. Then eventually, what you really see in the Dynamo is really nothing. Then you only need to set really, really small problem throughput. That's how you can also save the cost. Again, this is kind of demonstrated use cases we just want to share, but you can imagine how, based on how you actually define this configuration of the clusters or systems, you can achieve a lot different the goals and then the rewards coming from that. So far we actually talked about the read hashard. What about write hashard? In typical, this is more critical problems because although you set the eventual consistency setup in your Dynamo table, the write cost is 20 times more expensive than read. So like usually, although you set like really, really high problem throughput on read, it's not dominating compared to the write cost. So let's say app services actually start sending the massive writes for whatever reason. It can be bot, it can be spam, it can be completely unexpected data access patterns. It started hammering out the DynamoDB. What should I do? Again, you can actually set really high problem throughput to overcome, but that's really cost ineffective. So this is one way you can actually handle that. As soon as you actually start receiving those massive requests in the right side, you can sending those requests and redirecting to the queue. And you can actually maintain your own worker set. It can be, again, KCA workers. It can be just regular worker consuming the message from SQS queue. It can be Lambda function. It's really your choice. But keep in mind, if you want to maintain your own work on EC2, please consider using spot instances. That's a best practice. You actually can save cost more. But obviously, that means your operation should be idempotent. Whenever you repeat them, you should be able to recover them as it is. And the queue side, I just showed that as SQS, but you can just choose DynamoDB. It can be Kinesis. It's really up to you. One important thing here is, then why not just like using this everywhere? It's not. Because usually this asynchronous operation is slower than synchronization in terms of data sync. So if you really need real-time consistency, relatively speaking, then you want to handle it in a synchronous way. So you really, what we usually do in practice is you identify the track patterns, what's the requirement in terms of the speed of the consistency required, and then identify a specific path, and only allowing the rate limiting concepts for that particular path. Rest of the cases, you can actually apply the same synchronous rates. And Dynamo will be happy with that even with autoscaling. So one message I really want to deliver throughout this simple example is there are many different best practices around, but you really need to understand what that actually means on your data set and in your service. Once you understand fully, okay, based on this access pattern, there's this particular path, maybe 20% of the path should we go to this rate limiting, 80% of the writing is totally fine. That actually gives me, on average, maybe 80% of provision throughput consumptions achieved. That's great. Same thing happening for the read. So in summary, we just want to say, whenever you see the hot shard, this is really hard to avoid. You just need to come up with a systematic way to avoid them. And obviously, if you can come up with a perfect key design, that's absolutely great. But again, it's really tough. So that's pretty much it that I actually want to share today. What we covered at a higher level today is why massive migration is required, what actually means, what is the goal of the property we want to achieve throughout that procedure, how we actually achieve that in a more reliable way. And this is what we actually achieved, and this is one of the indicators that we actually got that higher level. Again, this is just an example, like what actually means in real world. There are many different indicators we actually need to analyze that. But if you step back and then looking at this, not just like simply just step, you will see the users are getting happy. Once you actually improve your performances underlying, we didn't change anything, but suddenly app is getting faster and then responsive. Then all the rates on the app is immediately reflected. That's great to see. And at the same time, within the Tinder teams, we have a lot more freedom to build the features really quickly and in a reliable way on top of the provided backend service and data stores. Then it will actually give back to the users, hey, this is a great feature, we actually built it. It works in a really reliable way that actually make more impact on user side. It comes back to us. So you can understand this ecosystem cycle. That's something we actually want to achieve, and you will see at the end of the migration, you can achieve this same thing in different way or your own defined way. So this is just one picture that we actually took from one of the boat trips in LA. This is part of the colleagues, the great colleagues we actually working together, including ops team too.
You guys are having too much fun.
Yeah, we drink too much. So please check out the website as well if you're interested. Then I think I'm happy to open up the Q&A.
Yeah, I do want to just say one last thing that I think it was a little dramatized story that I said, oh, let's hire JunYoung to do all of this. And obviously, it wasn't himself, as a whole boatload of people right there. So it was a great team. Many of them are here today. I really want to thank my team. They're just so awesome. And and it was amazing. And last thing is the learnings we shared today, we actually learned it in the hard way. For example, we started with one-way data validation. Of course, the data in the original store, in the new store were all good. And we later learned, and yes, the original data is in the new table and some. So, and then we learned we need to do two-way validation. We actually just, went back to square one and restarted the whole process. Don't feel bad about it. Anticipate you will need to take a couple try, but kind of with conviction, with diligence, with attention to detail, you will get there. There is a light at the end of the tunnel. So we're opening up for questions, and thank you so much for your patience in sitting through the presentation. There are 2 microphones in the hallway, so please come up, form a queue, and ask your questions. Thank you. Go ahead.
Hey, so my question is with the complex queries that you have. When you do a MongoDB collection query to a DynamoDB table query one-to-one, I mean, those queries require a lot of indices on DynamoDB tables to be matching one-to-one.
Yep.
So how did you go about designing those? Because the more indexes you add, it's slower and it costs you more, and then.
Totally. That's a good question. So the one caveat here is Dynamo has a lot more limitation in terms of index extensibility. So in Mongo, you can actually maintain whatever number of indexes. But that's also bad because implicitly you get the penalty. And then user doesn't really recognize that often. So keep adding the indexes and getting slower and slower. Once you bring the more data, it's getting worse. As opposed to Dynamo, they explicitly limit them. So what we need to do is analyzing what index set we really need to keep them. Analyzing, do we need to maintain as LSI or GSI? Migrating them. If some of them can be dropped, that's great. If we still need to support some of the specific join-like indexes, then you have to flatten the data again across different tables and access differently. When I say validation, regardless of how you actually physically design, distribute data, you have to aggregate again in the final form and then compare. So it really depending on how you actually handle this business logic. Does it answer your question?
Yeah, thank you.
Yeah, take one on this side. Yeah.
Okay, John and Maria, first thanks for the very impressive session. And I work for Symantec for user protection. We are actually experiencing something very similar, but we just started for the data migration from relatively traditional store RDS into something like NoSQL out there. I'm just curious, in your migration, I would imagine it will take several months, right? The whole process. Do you have a need to maintain the data consistency among those 2 data stores? And what is how you strategically achieve that?
Yeah, the answer is absolutely, right? Because we do have a very high requirement that for data consistency, it is our users' data, and we need to keep it 100% consistent. And that's why we built this 2-way data validation and then a gradual cutover. And so when it's 100%, we're all happy, and we made the cutover.
If you don't mind, I will follow up from there. I think those 2 data sets, they're then in dynamic nature. So every second, because you have billions of transactions every day, so every second they will be different.
Yeah.
I know actually there's also other things out there. The whole thing is a heterogeneous data store.
Yeah.
I don't know there's a transaction there out there. So what if actually after 3 weeks, do we still have the confidence they're in sync?
Yes, we do online validation. It wasn't an offline validation. That online validation means every read and write comes in, and we query both stores, the original and the new, and we have a system that says score is 100%, it's green, and JunYoung shares that service is fully instrumented, so we do have the confidence that it's 100% consistent.
The online ones, you will hit actually the real the traffic.
In runtime, yeah.
What if actually you have another M percentage of them, they are not actually touched for 6 months? So how do you know they're in sync?
So that's covered by offline validation. That's why we need both.
So if you, for the offline ones, do you iterate through every
data?
Every data out there. So you have a way to iterate it and without any actually slow the system down.
Exactly.
Yeah.
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 I see.
That's more like offline job.
We really invested in the validation service. We basically built a new service just to do this. And of course, after you invested in this, and now we're freed from migration. We can migrate with confidence, and it's very agnostic to either it's from Mongo to Dynamo or whatever, from one destination to another, that you can do that.
I would imagine actually there's also a detail where you do the offline validation out there. So at the very moment, there's a live traffic hit one of it. Actually, they're different at that moment. So you will think, okay, actually I have one data here. I don't have this exactly data there. But maybe after 5 seconds, you go back and look at them. They're now the same. So
the eventual consistency.
The eventual consistency,
Yeah.
right? You deal with all those things. Okay.
That's true.
Yeah, but for us, it's not 5 seconds. I mean, that's too long. Yeah.
That's why
Probably within milliseconds, it will be consistent.
Thank you.
That's why we repeat multiple times for the validation, not only one time.
Yeah.
Just like making sure we actually see the criteria satisfied consistently. Then that's where you can actually say that on every side, you can actually good to go.
Yeah.
Thank you so much.
Thank you. Yeah, we'll take a question on this side.
Hey, so when you were doing the cutover to actually start driving like production traffic for both read and write on Dynamo, what kind of metrics were you looking at to determine that it was actually working properly?
So there are many different metrics we actually measure that. For instance, whenever you maintain one table or one service, like literally speaking, we have more than 20, 30 metrics we actually maintain, and just maintain in one dashboard. That actually real-time way just show all the differences. Example of that is what is the P50 latency? What is P90 latency? What is P99 latency? What is the percentage of the data validated out as opposed to matched versus not matched? Why not is matched? Is it like missing or different? We're actually like measuring all the different reasons as well as a label, and then counting or measuring the metrics separately.
Okay.
It actually tells you what's going on really in the real world side, like in the data side.
Okay.
And also, we keep checking the cost as well. That's the kind of side one though, but that's a very important thing as well when you actually build a new table.
Of course.
So that's just an example, but it's really dependent on your success metrics.
Makes sense. And just a quick follow-up, you mentioned you spent a lot of time obviously on this data validation thing. What kind of scenarios did you encounter where validation failed?
Validation failure, you mean?
Yeah, like what drove those?
So some of the example is we have, like if you really, it's really case by case, but if you rely on the data, like stream for instance, from the queue to catching up the failure cases, it only has a 24-hour data retention period. For whatever reason, your worker kept failing, then you immediately lose that permanent way after 24 hours. Okay. That's one thing you can actually start seeing the inconsistency. So sometimes we realize that this automatic catching up doesn't really work for certain types of data because we have to do manual intervention for that case. It can be legacy data, it can be very noisy.
Yep.
So for whatever things that we actually continuously failing, we actually log them out, like just all the IDs, and then see what's different.
Yep. Yeah, it could be caused by unanticipated data issues. Race condition was another one. We
Yep.
ran into a couple of those, or in a high throughput scenario, you ran into race conditions. And also data loss for various reasons that you have data loss. Yep.
Okay. Thank you.
Thank you.
Hi, I have a question. So I'm not that familiar with DynamoDB and the design, but I'm interested in seeing that the schema for the queue that you use as a queue, is it different from the target schema, or is it based on source schema? Is it post-transform and before transformation?
So in general, I highly recommend you only maintain ID and timestamp in the queue for the failure cases. Sometimes it's very efficient if you just store the snapshot you're actually trying to write or update, putting in the queue as it is, catching up. That's great in terms of partial update perspectives. But in terms of cost, again, it's not different from the Dynamo model.
Yeah, the question you're asking, in what data schema we should store the elements in the queue? Was it a pre-transformation or post-transformation?
Yeah, or maybe change that, like delete or insert. Is like is its own schema, or is it conforming to a target schema?
Yeah, I think they're both approaches are valid. It depends on if you have low confidence in if you have very complex transformation service and you think the transformation service would be causing issues either in delaying or throwing exceptions, you might want to store it in the pre-transformation, so you can retry to retransform. If it's a very simple transformation, right, you're very confident that's high success rate, then you store it in the post-transformation. We store in post-transformation format.
Yeah, in that, yeah.
Thanks.
All right, one last question.
Yeah, with respect to the caching use cases, on the DAX use case, did you or are you able to selectively cache different tables? Like I could imagine some tables you don't want to cache.
So it's really, again, when you actually set the DAX, there are many different ways to actually utilize them. One way you can do is maintain DAX separately per table. Another way is you can actually share one DAX cluster across all multiple tables. Only when that is enabled is when you set the endpoint and then sending that traffic to the target table through that. That is only time when actually utilizing the DAX. For instance, let's say I have a table A and B. I only want to utilize DAX on the A but not B. Then when you actually access the Dynamo data, in A, you can only selectively set the endpoint of DAX, dynamic way. And then B, you don't set them. Then you actually straightly go to the Dynamo table and then getting back.
Okay.
And as opposed to A side, you're actually implicitly going through DAX because you actually set the endpoint. And that's how you actually control the traffic.
Okay. Thank you.
Yeah. Great. Thank you, guys.
Thank you so much.